the concept of a family is very important in real life. In mathematics, the concept of a family is captured by the idea of a set. In this lecture, we shall look at making this idea of a set more concrete. Basic properties of sets. What we can do with sets. The idea of a collection of things is very, very natural. So, for example, we've got a pack of dogs, a bunch of grapes, and these are all examples of collections of things, or a family of things. Now, so a set in mathematics, a set of things, is what captures the idea of, is defined as this simple collection or family of things. Okay, so the idea of a set is essentially the idea of a collection or a family, okay? And once you've got a family, one can also view it from the point of the thing in the family. So this brings us to this idea of belonging to, which in mathematics is what we denote by this epsilon symbol. Okay, so for example, we say that a wolf, a dog, you see, belongs to the collection of dogs or the set of dogs. See, so this is just saying the same thing from the point of view of the thing. Okay, and so in this case, we so in this case, what happens here is that let's say that we denote the dog by X and the set of dogs by A, then we write this as X belongs to A. Okay, that's just mathematical notation. Right. Now, if X does not belong to a set A, then we just say X does not belong to A. Okay. So this is notation. Okay, so now in mathematics we have standard notation for standard sets. Okay, so N is, this is what is called the set of natural numbers. Okay, so these are all the numbers starting, the naturally counting numbers starting from 1, 2, 3, 4, 5. Okay. So in this case, we can say that 1 belongs to N, but a half does not belong to N, the set of natural numbers. Okay, so this idea of belonging to is very natural. Okay, now we move on to the idea of what is called the equality of sets. Now, if every element, okay, so suppose we've got two sets, A and B. How do we define whether these two, the definition, how do we know whether these two sets are equal, okay? Or whether the two families are identical. When are the two families identical, okay? So now this happens, okay? So this obviously happens when the thing that the things that are in family A are actually in family B. Okay, so they've got identical things. Okay, so now, so so the things are what we call elements, yeah? So remember that now, okay, so the things in your family are called elements, okay? So if every element of set A belongs to set B, this we shall write as A is a subset of B, okay? Or same notation is B is a subset of A, okay? So if every element of A belongs to the set of B, okay? And at the same time, so we also want, so if A and B contain the same elements or the same things, if then these two families are identical, okay? So therefore it also requires that every element of set B also belongs to set A, okay? And this we write as B is a subset of A, or A swallows up B, okay? Those of you who have come from high school should have seen this as a Venn diagram, okay? So A is a smaller set of B, then every element or everything of A in family A is found in family B, okay? So therefore, we say that the two sets or the two families are identical exactly when A is a subset of B and B is a subset of A, okay? So this requires every element or everything in family A to be found in B. And the second proof, so notice there are two proofs that are needed to prove that the two sets are identical. That every element of A is found in the family B, and conversely, every element in B is found in set A, okay? So that is when we establish whether two families are the same, okay? So the next thing we then move on to is the concept of defining a set. How do we actually define a set, okay? One way in which we can define a set is by listing the elements out, okay? So there are only two ways, okay? So the first method is what is called listing. So let's say A is the set of the first three counting numbers. Then we just list them out, 1, 2, and 3, okay? Likewise, the set of all natural numbers is all the counting numbers. So it's 1, 2, 3, 4, blah, 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 blah. The set of all integers is going to be, that one includes 0, 1 and minus 1, 2 and minus 2, 3 and minus 3, blah, 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 blah. So listing is a way in which we can actually define a set, okay? The second method that you also can define a set is by using what is called a predicate or what is called a property. So these guys behave like bouncers at a nightclub. They basically decide who comes in to the nightclub or who doesn't, who comes into the set or who comes into the family or who doesn't come into the family, okay? So for example, if you look at the set of fractions, okay? So these are all numbers of the form m divided by n, such that, you see, this means such that, okay? You can either use bar or dot dot or semi or full colon, doesn't matter, okay? Such that m and n are both integers and the denominator n is not allowed to be equal to 0. You see, this is what is called a predicate, because it sets the condition it sets a bouncer on the door of the set, which allows certain elements to be fractions, okay? Now, having now defined the equality of a set and how to define sets, okay? We now look at the idea of what are called set operations on sets, basic set operations on sets. What can you do with sets? Now, you see, that is how you make the concept or the idea of a set come alive. So for example, if your little brother asks you, what is a number? You'll say, well, it's something like 1 and 2, okay? And but then when you actually, now if he says, well, can you explain that deeper? You can go deeper by explaining to them, you can add, multiply, and divide numbers. And in such a way, the idea or the concept of a number becomes sharper. In like manner, these set operations define what we can do with sets. And thus we can get a sharper idea of what a set really is, on the concept of a set. So the first one is what is called a union. So what is A? If two sets, the A union B, so what we do here is that given two sets A and B, so we start with two sets A and B. Then we construct a third set called the union set, which we denote as A union B. So the sum, so the union is the idea of summing or adding numbers. It's the analog of adding, okay? So you pull all the elements of A, all the elements of B, and you merge it into a new family. That's the sum. So therefore, this is a new family, elements X, such that normally you use small letters for elements or things, such that X belongs to A or X belongs to B. Now remember that in English, especially like when we were small, our daddy used to say, do you want chocolate or ice cream? And it was exclusive. You couldn't say, I want both, okay? But in set theory, this thing is now used in an inclusive sense. So it basically means both can even be true, okay? So it's the elements that it's either in A or B or in both of them, okay? So that is the idea of pulling two sets together to get a larger third set called the union set, which we denote as A union B. So this is called the union set. So it's the analog of adding numbers. So just as you can add two numbers, and now the idea, the next one is what is called intersection. So if I have two families to start off with, A and B, I can form a third smaller family called A intersection B. And these are all the elements or the things such that this element must be found in both A and in family B. So X must be common to both family A and family B, okay? So if you've got a Venn diagram, okay, so therefore A union B, okay, this is the pooling of two families into a larger union family. Now, the intersection of two sets is all about where we actually find elements that are common in both of them, okay? So in this case, if I've got two sets A and B, it's the set that is actually common to both of them. That is A intersection B, okay? And then the next one which we have is what is called the complements of, let's say if I've got two sets A, B, the complement of A and B is like the subtraction. So this is like the subtraction of two numbers. So I can subtract set B from A. So this consists of all the elements X such that X is in A, but X does not belong to B. So this is the idea of the complement of two sets. So if I've got two sets A and B, so it's going to be all the elements that are actually in A but not in B, okay? So in this case, it's just going to be this shaded area, okay? So you're subtracting from A those elements that are found in B, okay? So this is a kind of like divorcing the two families, okay? The union of a two set is marrying the two families, and the intersection of two sets are just finding the common point of the two distinct families. Okay, and then also the idea of the zero set, you see, because that is like the number 0 is special. So that is that number which if you subtract or add it doesn't affect the number. And so the idea of that is the empty set. So this set actually has got no elements at all. It's like a vacuum. Okay. And when you've got an empty set, it basically allows you to describe when two sets are disjoint, when two families have nothing in common, and that is when their intersection is identically equal to the empty set. Okay. Now, so now actually, so just as in numbers where you can add just more than two numbers, you can do the same. You can have multiple unions and intersections of sets. Okay. So for example, if let's say that, so remember before we only started off with two sets. So now I start off with finitely many sets. So it's A1, A2 all the way to AN. So I've got n sets. Okay. Then how do I actually add n numbers together, just as in numbers? Okay, same thing. You just pool all of them together. So the pooling all of them together is we denote it as AI, where I runs from 1 to n. So this is called the union. So it's the same as if you got n numbers, A1, A2, and AN, and we add up all these numbers, A1 plus A2 plus AN. And remember, in high school, you just wrote it out as AI, where I runs from 1 to n. Okay, same thing. Okay, so this is the multiple union of the sets, and likewise the multiple intersection of the set. So this element is found, so this consists of all the elements that are found in each and every one of these n sets. So this is similarly called I equals 1 to n. Okay, right. So notice that we can actually write this out in set membership form. Okay, it is those elements such that x belongs to AI for I equals 1, 2, all the way up to n. Right. Now, to finally wrap up the lecture, we bring about the idea of a Cartesian product, because this is probably the closest idea to a product of two sets. You see, up to now we've had the zero set in the analog of the zero number as the empty set, and we've also got the analog of the addition of two sets as the union of two sets. But so far we haven't found an analog of the product of two sets, and this is done by the Cartesian product of two sets. Okay, so we start off with two non-empty sets. Okay, just like two numbers. Now we want to define what is in fact the product of these two sets. Okay, so in this case, the product of these two sets is the set of ordered pairs AB. Okay, so so remember the order is important. Okay, so for example, 0, 1 is not the same as 1, 0, because the 1 appears first. I mean, you've only got two elements in both ordered pairs. It's 0 and 1, 1 and 0. But notice that the order is notice that the 1 comes first here, the 0 comes first. So the Cartesian product A times B is going to be where A comes from A and B comes from B. Okay, so let's have an example of this. So let's say that our set is equal to 1, 2, and our set B is equal to 1, 5, 4. Then the Cartesian product of this set, okay, let's call it ABC, just so that we can have distinction. So A is the set of numbers, the first two numbers, and B is the set of the first three alphabets. Then A times B, or the Cartesian product set, is the product set, is just going to be, it's going to be 1A, 1B, 1C. You see the ordered pair, and it's going to be 2A, 2B, and 2C, and then 2B and 2C. Okay, so notice that what has happened here is that, notice that A and B, A had two elements. We write this as cardinality with this double sign. So this means the size of A was 2 and the size of B is equal to 3, or the cardinality of B is 3. Then notice that the size of the product set is going to give you 6. See, so this is the closest analog we have to the Cartesian product of two sets. Okay, so notice that there's a systematic way in which you can actually do that, and that is you can list out all the elements of A, 1, 2, and in this case you can also list all the elements of B as A, B, C on the vertical column and the horizontal row. Then A cross B is just going to be 1A. So actually it was even better to actually do it the other way around. So what we have here is that we've got AB. So A is going to be 1, 2, and B is A, B, C. This is better for teaching purposes. Then the Cartesian product is going to be 1A, 1B, 1C, 2A, 2B, and 2C. Okay, so that's how you construct it. And the way we can visualize this is simply by actually taking it's thinking of we can visualize this in a better way, in the following example. Okay, so let's give another example. Let's look at example 2. So in example 2, let's say that our first set is this open interval 0, 2. So these are all the numbers that start from 0, starting from 0 but excluding 0, and up to 2. So all the numbers starting from 0 up to 2. Okay, so if I can depict A as the set which starts from all the numbers starting from 0 up to 2. So that is A. Okay, set B, let's say set B is going to be equal to the open interval 1, 5. So this is the notation for open interval. So this means all the numbers x such that let's use y now. Y such that so let's call the elements in family B y. So these are all the numbers which start from 1 and end to 5 but excluding 1 and 5. Okay, that's why this word open simply means you don't include the end points. So B is then going to be starting from 1 all the way up to 5. Okay, so this is 1 all the way up to 5. So in this case, notice that A cross B is actually a rectangle, you see, whose a rectangle with base 2, you see that, and what, height 4, because it's going to be like this, you see. So this is going to be, so this is B and that's A, and this is A cross B. So this is the Cartesian product. So this is a rectangle whose base is 2 and whose height is 4. Okay, and notice that the area of this is actually going to give you what, 8. And notice that the length of A, notice that the length of A, or the width, is actually 2, and the length of B is actually going to give you 4. And notice that the area of actually turns out, can measure the size of your of your Cartesian product. So notice that this is the Cartesian product of two open intervals, so two sticks. So A is a stick, you see. Notice that A takes the shape of a stick. You see, it is this red stick. And then B takes the shape of this blue stick. Okay, so A and B are both sticks, and their Cartesian product is a two-dimensional object or a rectangle, which I will just color in with yellow. Okay.